Perché c'è questo che parli qui,
sì.
però è in rete. È in rete, allora in rete, adesso bisogna capire... Sì, bisogna capire se c'è l'Arsen però. Prova a parlare.
Quindi,
Ciao.
quindi usi il gelato dopo. Sì.
Funziona.
Tu usi il gelato?
Non lo so, no, non uso niente. Ma quello va bene.
Con questo va bene.
Ottimo.
Però devi stare nell'area.
Sì, sono...
Però non lo sento in rete.
Con il gelato?
Con quello.
Con quello.
Allora devi stare
Col gelato.
Va bene, mi congelerò.
Okay, it is a pleasure for me to introduce Professor Elio Tosatti, who is very well known in our community, since he has been one of the founders, let's say, of solid state physics in Italy, indeed, and he has spent his career in several places, including Rome, but especially in Trieste, at SISSA and ICTP, of which he has been also the director. He has won several prizes, including the Fermi and the Tate Prize, and his research has spanned over several subjects, and in the last years especially on the subject of friction, which is very important from the technological point of view, but it poses also several basic science problems. And today he will show us some aspects of this research that is also within a ERC project that he has won in the last years. So thank you, and we can start.
Thank you, Riccardo. And we have to switch this off. Cosa bisogna fare?
Questo va spento?
Questo a toccarlo, ecco.
Ecco qua.
A toccarlo. Okay, so thank you very much. I speak English because I understand there are people that would benefit better this way. So I'm going to tell you some of the things that have occupied me and part of the group in the last few years. And this has to do with friction from the point of view of a physicist, not from the point of view of an engineer or a tribologist. There is a huge community that deals with friction since a very long time. We do not belong to that community. We are condensed matter physicists, but we try to explore the physical aspects of the phenomenon. Before I do that, let me just start with a joke, because the rest might be rather boring, so maybe you get something interesting from the beginning. The Economist recently introduced a similarity between Italy and Britain. This would have been an insult, maybe it still is an insult within the the UK community, but it seems that instead of Italy moving towards serious behaviors, as it used to be the case in the UK, it's the UK that is moving towards our kind of behavior this way. Similarly, there is another analogy between Britain and Italy, and this has to do with the city of Bristol. Now, I don't know if you've ever been to Bristol. It's a very nice city. According to Michael Berry, Sir Michael Berry, everything in physics begins in Bristol. Everything in physics important has been done in Bristol, started in Bristol, developed in Bristol. Okay, I don't know if he's right, but certainly Mott was in Bristol, and many other people have been in. Frank was in Bristol, and so on. You could say something similar about Genova. I'm not joking. If you just go back and see who came from here and who went here and who did something, at least in our field, they have to do something with Genova. I'm not trying to attract wishful thinking from you, but there is a certain analogy which I think is a better analogy than the one before. Okay, so this is Genova versus Bristol in analogy with the other thing. Now to our business. I will speak to people that I assume will not know so much about friction, so I feel that I have to introduce the subject. This introduction will, of course, be boring, because friction is not a fashionable subject. it was not in the past. It was a very boring subject in the past. Now it is slightly better, but not many people are knowledgeable about it, so I feel that I have to do some introduction to this, and then I will get to some of the phenomena that have become clearer in more recent times, and maybe I'll talk about graphene and twisted interfaces, which I think are on the highlight from the electronic viewpoint. And what about the mechanics? I'll talk about the mechanics of this system. Now, if there will be time, and I don't think there will actually be time. So in fact, I hope that our chairman will sort of wave his hands when it's time to wrap it up, right? But if there was time, I might venture into these other things, quantum lubricity, or towards the theory of friction, that are sort of more speculative. Good. So certainly a theme that is very hot in these times, in this century, I would say, is non-equilibrium physics. The equilibrium physics belonged with the 19th century. It was explored extensively over the last century, and now we are into the non-equilibrium world, both from, say, electronics, on the point of view of superconductivity under high excitation, for example. The active matter is mechanically very important and very promising, also in connection with bio things. So non-equilibrium physics is à la page, it is important, and it is more difficult because we don't have the same instruments for systems out of equilibrium as we do for systems in equilibrium. In equilibrium, you write down, you say, I have to have a Hamiltonian, I have to have a ground state, I have to have the excited states, I have to have a statistical partition function, and all these things exist. And whether you can access them and measure them and so on is another matter, but the thing is very clear. If you're out of equilibrium, yeah, in principle you have an equation of motion. Yeah, in principle you have a principle of minimal action. But when you come down to doing the same kind of approximate approaches that we do in equilibrium, Ginzburg, Landau, and this and that and the other, you immediately find yourself at a loss. So non-equilibrium physics is developing and is more difficult. Now, mechanical non-equilibrium is the less popular among these things, and this is what I concern myself with. This is the simplest form of mechanical non-equilibrium, and of course everyone has heard about it, pushing something. And this is one of the many nano friction type of experiments. I will not go into any details about any of these experiments, it's not my job, but typically you have, say, some point and it moves over a well-defined piece of surface of nanoscopic size, and you can measure the amount of friction in there. So that's a nanomechanical type of measurement. Now, I show this slide because it shows not only the fact that people don't care about friction, but it shows that the community of theoretical physicists has been very strongly prejudiced against studying this material. Larkin and Khmelnytsky are well-known theorists of the former Soviet Union. Larkin is dead. Khmelnytsky is still alive. It happened that they were studying flux lattices in superconductors, and they made a paper in 1978 that was dealing with friction because they saw an analog between the motion of the flux lattice in a superconductor and, say, friction of lattices and so on. They wrote a paper, and they submitted it to JATP. Where do you submit it if you are in the Soviet Union? And then they got a letter from Lifshitz saying, no, please, take it out. Take it out because if we publish it, it did not question that the paper was right or wrong or anything. But if we publish it, then a lot of engineers will send us papers, and we do not want them. Right? So this shows that the prejudice, interdisciplinary, with a negative sign in front. I think this is a very good example of a wrong type of interaction between fields. Nowadays, this thing does not exist anymore. Okay, so we can deal into friction and not be completely disparaged by our colleagues. Now, friction between solid bodies has many, many different types of form. The first one on top, I could call this the Ferdighini friction. That is, you have wear. Ferdighini is now working on his on his house. He has to clean up something, and you apply friction to remove the crud from his things. This is the most common type of friction. It is not very exciting from the point of view of physics, and I will not particularly study this type of friction. Of course, it is very important. Of course, you can study, but people that have not found something so fundamentally important from the point of view of physics. I may be proven wrong tomorrow morning and say, you dismissed this thing and it was very exciting. You did not understand. What we tend to study mostly is dry phononic friction. You slide on something, you do not take anything away. You just provoke some work. You do some work. This work is dissipated into the system. It warms up. The system is conveyed away in the form of phonons. That is what I will mostly concentrate upon. But there are many other types of friction, of course. There's viscous friction, so lubricated interfaces. That's a very common type of friction, even without wear. That's certainly very important. There is viscoelastic dissipation in the car tires. That's very important. You know that you have to change your tires when you go from summer to winter, because the viscoelastic property of the tire rubber changes, and this friction happens not at the surface, but it happens inside the tire. It's a rather important thing from many viewpoints, including some physics viewpoint. We could discuss this, but I will not discuss it further. There are electronic and magnetic and quantum effects in friction that have been approached and studied, and that's again another subject that could be discussed. There's even a friction in vacuum. If you have two surfaces separated by vacuum, you might argue, how can friction occur if you have vacuum in between? Well, it can occur because the two surfaces interact with each other via Casimir-type forces. The vacuum is not vacuum. Vacuum is not empty. There is an electromagnetic field inside. And the photons, the virtual photons from one system to the other, take some time to go and come back in order to realize the Casimir effect. If you move the two surfaces very fast, then the photon that comes back does not meet the place where the photon came from in the first place. As a result, the Casimir attraction disappears. You move two surfaces very fast, and the Casimir attraction goes away. If the Casimir attraction goes away, the energy goes up, and therefore you have to pay for it, and that's some kind of friction. And you might invent other types of friction too. I'm not going to talk about anything else except the one in the red lines here. So some of the themes I'll cover. I want to review the theoretical approaches because this is the kind of business in which I'm in, and I feel that one should talk about things that one knows, and to give you an idea of what we do. Then we can use then friction to discover things. Usually you do not think that with friction you can learn a lot about what you have under yourself, but in fact you can. You can transform it into a spectroscopy. I think that's rather amusing, and I want to talk about that. The 2D materials are very peculiar in friction because they're very flat, they're very adhesive, they're very popular these days, and I think they open a practical chapter in the physics of friction that is worth exploring. And then there will be other things, quantum effect, collective phenomena, and so on. And I don't know if will be time to get there. So let me talk about nano friction. Really, the turning point for friction from the viewpoint that I approach has been in the 1980s. In the 1980s, the tip-based instruments were invented in IBM Zurich. And first of all, they did the spectroscopy of surfaces. They're finding out the corrugation and so on, the shape of surfaces. But then immediately next to that, Binnig and others explored the possibility to observe friction at the nanoscale. And here is an experiment done in Basel, although it was done in Basel, but there is here a Genovese co-author, Enrico Gnecco, who is the first author of this paper, where they have a surface of something, sodium chloride, I believe it was, and you pass this tip back and forth, and if you can measure the force by measuring the tilting angle of your tip, you end up with a picture like this one, the zigzag. It shows that there is atomic stick slip. When you go to the right it goes this way. When you come back, it comes this way. The area inside this curve, it's a force displacement. So the area inside is an energy. And the area of this is precisely the energy dissipated in a single cycle. Okay? So you measure the friction very directly. And the zigzag has to do with stick slip. The tip is not sliding continuously, but it's jumping like tack, 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 just by successive jumps. So stick slip friction. That, of course, is very easy to model by models that have been invented long before, and it's the simplest model on Earth. You have a slider here in the point of a point, and attached with a spring, and the stage moving with velocity v, and this would essentially model the same kind of physics that you access with this experiment. There are other experiments they do now with layered materials. You slide a piece of graphite on top of another piece of graphite. Of course, when you slide this way, it tends to slide back because the adhesion energy wants it to go back. And you can study it as a function of twist angle, velocity, temperature, and so on. It's no longer the friction of a point-like tip. It's the friction of two interfaces, and I'll be concerned with this later on. Now, what kind of theory do we have for this system? The experiments exist, and the experiments are those that motivate us to move forward. We lay behind the experiments. Experiments have come, and now we have to understand them. First of all, we have the empirical laws that have been known for many centuries, beginning with Leonardo da Vinci. Then there are more recent things, but not so recent, say 50 or 60 or 70 years ago, phenomenological laws. They have been developed mostly by people in geophysics. They wanted to describe the friction of tectonic interfaces. After all, earthquakes are a problem in friction. The two plates stick together for a while. When the stress exceeds a certain static value, they jump, and this fracture produces friction and also produces a lot of damage. So there's phenomenological treatments of friction developed by statisticians. And then there's a theory. What theory to do is a good question. I will talk briefly about it, but we don't have too much in the way of theory. There is a fair amount under construction, something to be done. In fact, I found points of contact here with things that are being done here in other fields, building a theory for a very complex system. The main tool that many of us use these days is computer simulation, molecular dynamics simulations mostly. Because of course, as everybody knows, in simulation you build up a prototype system, you control all the parameters, you do your simulations, and you try to learn by changing the parameters, by using whatever understanding you have, whatever theory you have, to learn them. There are, of course, two main limitations here that are size and time. Size, because in friction of two sliding interfaces, you would not like to be limited to a few thousand particles. That's very small, and the real sizes may be much, much larger. But the main limitation is time, because we can, in molecular dynamics, with modest computing means that we have and so on, you would not go beyond, say, 100 nanoseconds or something like this, and many, many phenomena take much longer to be described and understood, and then you have to try to get to extrapolate what you measure what in the simulation with these short times to what happens in real life, maybe on a very much longer time scale. And the last tool coming in the order is emulation. Suppose you want to describe a very complicated system for which you have equations, but you're not really able to solve them or to extract all the juice there is in it. If you change the parameters, you can design an experiment that will realize this idealized system. So you do not measure the friction anymore. You build an experiment that is supposed to realize a certain equation. This sounds a little, how should I say, strange. It kind of sounds a little funny, but it turns out that all these things are very, very informative. I will describe some of it. This is experimental work, emulation, but it is emulating something which is dictated by the theorist. So I talked about the empirical laws. This is what one learns. I'm a perito industriale, so I was learning these things, of course, in my courses in the afternoon. I was listening to the Ferrari running in Modena next to my school, and I found these things very boring, but this is what they are. Friction is discovered by Leonardo. Friction is independent of contact area. It's rather strange, isn't it? I mean, something which is broad like this and something which is narrow like this, the friction of two pieces of wood, this is what the experiment of Leonardo would have done, is about the same. Very strange. Well, in the macro world, it may be like that, and there is some understanding behind it. It's because when the weight is bigger, the compenetration of the two surfaces gets larger, and therefore the friction over a smaller area, but is larger because you have contacts that are more intimate. And roughly speaking, the two things compensate each other. In the nano world, this is not true. The friction is not proportional to the area. It depends. Friction is proportional to normal load. Once again, this has to do with this interpenetrating of surfaces in the macroscopic case. In the nanoscale experiment, it's not true anymore. Friction is independent of velocity. I think this was described by Coulomb, the same of the Coulomb law. This is a very funny phenomenon. You push something, and you need to reach a certain force, which is called the static friction, and then these things begin to move. When it begins to move, the force that you have to apply drops down by a factor of about 2. So once it moves, it begins to move. You can keep it moving with a smaller force, but then if you want it to go twice as fast, you don't actually have to apply a force which is a factor of 2. It's about the same force. So the growth is only logarithmic, very, very gently smooth. And the reason for that is that in most cases in nature, the sliding occurs by stick slip, like I showed you before, this zigzag. If you want to go faster, what happens is that the stick slip frequency increases. So zap, 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 it goes up faster, but the mean value does not increase particularly very much. So you increase the frequency of the stick slip. If you were listening, you would listen to a higher pitch, if you want, for the stick slip, scricchiolio in Italian, but the friction would not go up very much. This is the reason why in the macroscopic world, friction is basically independent of velocity. In the nano systems, it depends, because in nano cases, you can also have smooth sliding. Smooth sliding is very, very rare in the macroscopic world, at least for dry friction. In the lubricated case, you can have smooth sliding, but without lubrication, sliding is very, very rarely smooth. But in the nano systems, it's actually possible to have smooth sliding. And so in those cases, the friction, first of all, it would be much smaller. Secondly, it would grow linearly with velocity. That's called viscous friction. Friction is related to adhesion. That depends. Friction has to do with corrugation, with rugosity, and that is certainly okay. But the adhesion between two bodies and the corrugation are not the same. They're not the same. Particularly, for example, in the nanomaterials like 2D materials and so on, the adhesion can be very large between two bodies, but the corrugation can be very small. And so it is not true that friction is connected with adhesion. In the macroscopic world, corrugation and adhesion sometimes play together, and so this can go differently. And the static friction is larger than dynamic. That is true in when you have sticking, because, as I said, you have to push something, and then eventually it will move, and the friction will drop by about a factor of 2. So, but that is true for stick-slip friction. If you have smooth friction, the dynamic friction can be very small. So the nano world has laws, if you wish, that are very different from the macroscopic world. In the end, one would like to understand what happens in this nano world. Secondly, it would be nice to use these things of the nano world to explain, to actually derive the friction of the macroscopic world. This has not been done yet. what does a poor theorist do confronted with this reality? Well, when a theory does not know what to do, he or she will do linear response theory. You say, well, suppose that my frictional event is a very gentle thing. I do it with a very kind of small force. The system is just unperturbed, and I apply a very, very small force, and the system will execute maybe a random walk. A nano system will do a random walk in finite temperature. And then if I apply a very small force, then the system will drift very, very gently. The random walk, the center of mass of the random walk will move very, very gently. And this would be the diffusive friction. This can be treated in this way within linear response theory. It almost always fails, but sometimes it works. I will show one example. And then when linear response fails, you have to go to something nonlinear, evidently. And stick-slip is a typical nonlinear phenomenon. So how do you study a system like that? Either you study it in the experiment, or you build up some model that will allow you to understand what is going on, to give you a clue for certain types of behavior. I think this is a trademark of physics, to build a model and to work very hard to understand the model, and then to use what comes out of a model to understand what goes on in the real world. Sometimes one has to even explain to people outside of our community why it is so important to understand the model. And the model is far too simple, everybody would say. Reality is much more complicated than the model. Yes, but if you don't know anything, the model will give you paradigms with which you can make progress. And in these simple models, we understand some paradigms: stick-slip friction, superlubricity, thermolubricity, Aubry transitions, Jarzynski, Freela, various types of things that are important, and they will remain important in the real world. And then there is, of course, simulation, non-equilibrium molecular dynamics, which sort of can address various types of experiments, and also can try to make contact between reality and some of these models. And then this theory, which is always the last thing to come about, and which is something perennially under construction. So let me show an example of linear response theory that by chance works. And this will be appealing here in Genoa, particularly because it is something which is very similar to people that here were doing helium scattering, and things that have been understood actually here in Genoa by groups that were doing helium scattering from surfaces. Suppose you have a particle here, this red particle sliding on a linear chain. You slide on the linear chain, the interaction is very weak, and but it is non-zero. And so as you move, the chain will vibrate under the thing, and you can solve the equations of motion, calculate the force felt as you move this particle with the velocity v, and you can plot out this friction force, the dissipated energy as function of velocity. And you can calculate and simulate, solve an equation anyway, and you get this blue curve. The blue curve shows that the energy dissipated goes down as you move faster and faster, but you get some strange peaks here. 1, 2, 3 peaks. What are these peaks? What is this fit? And why does the dissipation finish at some point? Well, what happens is that as you move the system, you have to consider the object which is moving with velocity v as a straight line in this curve, and every time the straight line will touch the phonon curve of the system, there will be a loss peak. So that is the same understanding that people doing helium scattering would have applied in the past, and this is how people measured here in Genoa the dispersion relation of surfaces. This is work done, say, more than 50 years ago. This is a simulation, so you might say, what about theory? Where is the linear response? Well, so first of all, it shows that these 3 peaks here have to do with these crossings. Every time you can match energy and momentum, then there is transfer of energy from the sliding particle to the system. So that's pretty straightforward. Well, the linear response theory is that you can make a Born approximation theory of scattering between this moving object and the system. And if you do that, you get a standard formula where your frictional force is proportional to a matrix element square of the interaction. Born approximation is like this in scattering theory. And you have some prefactor. And the prefactor contains a density of states that has to do with the matching of omega minus QV. It so happens that one of the chief author of this paper is Emanuele, who was a PhD student here. He did it when he came to Trieste, but it's another Genovese correction. And the amusing thing, which I did not expect at all, is that the result of this simple formula corresponds smack on without any particular deviation with the simulation exactly. They're identical. The two things are identical. So linear response theory in this case works very precisely. Maybe it is not a surprise because it is something in the limit where V is very small, but you can apply linear response theory to simple frictional problems of this kind, and you get the right answer. But there are not many examples like these that you could make. So let's go over to nonlinear. And nonlinear is these models that people work with. They are about 100 years old. They go back to Prandtl and Frenkel and Tomlinson and this and that. It's either a sliding point that will describe a tip-like experiment, or a chain, a harmonic chain sliding on a periodic substrate will be our one-dimensional mimic of the friction of incommensurate or poorly commensurate systems. Incommensurate when the spacing between two particles in this chain is different between the distance between two minima in this energy curve. Okay, so the Tomlinson model, the single slider, illustrates a very first thing. If there are two regimes, if you slide a single particle connected with a spring, the limit where the spring is stiff and the limit where the spring is soft. If the spring is stiff, then the total energy as function of position of the stage is a continuous function. It does not have any instabilities. So here you would get a friction that is proportional to velocity. There is no discontinuity, no mechanical instability, and the friction will be proportional to velocity. It will go to zero when the velocity goes to zero. There is no static friction. In this other case, no, I'm sorry, the static friction is there, but you still move with zero dissipation. In this other case, if the spring is very soft, then no. As you pull, the energy profile will have these corrugations, and then at some point you have to jump. You get a mechanical instability, so the motion will be stick-slip, like I was describing before. And in this case, the force will be logarithmic, and essentially, logarithm is a very slowly varying function, so basically independent of velocity. So even this very simple model can already tell you that you can have one type of behavior or the other. And this type of behavior, you can recognize it in any system. This morning I was hearing about very nice work of some water moving inside a nanotube or something, and it was clear that it could be interpreted one way or another according to this paradigm. The static friction simulated from the Tomlinson model is essentially similar to what they see in experiment. Now, the friction in these models has a very characteristic velocity and temperature dependence. Here is the Prandtl-Tomlinson model solved, simulation or calculation if you wish. You have regimes that are very different depending whether you are at low velocity or at low temperature. Here on the top where you see the red arrow here is the low velocity and low temperature limit. You see that here friction is, this is a log scale. So you see that here friction changes very little with changing velocity. This is the stick-slip regime. If you go very slow, if the temperature is very low, then you have this mechanical instability and you have stick-slip friction. And this is immediately validated by existing experiments. Enrico Gnecco and collaborators, they were sliding their tip on sodium chloride, and they had pictures very similar to this logarithmic behavior, okay? So the Tomlinson model is quite good for understanding what is going on here. But you can go to the other regime. You warm up the system, or you go to very high velocity. Both cases. What happens, you see, you veer over to this other regime here, where the thing has changed completely, and the slope in this curve has become a slope of 1, which means the friction is viscous, and there is no more any stick slip. In this case, high temperature or high velocity, you get into a regime, so high velocity, high temperature in particular. At high temperature, you get into a regime that you can call thermolubric. That is, you have a barrier, and the barrier would want to keep you from moving, but temperature will permit passing this barrier back and forth, back and forth, back and forth many times between an instant and the other. So a barrier that is being negotiated by temperature many times is cancelled in practice. You can move without paying because, so to speak, the bigliettaio is not there. You can enter and come out as much as you want. So this is called, by some people, Krylov and Frenkel, called thermolubricity. This is quite important. It's a very rare regime to be reached in the real experiment, but you can turn for a very sufficiently small system, you can turn stick-slip friction into thermolubric. That is, at very high temperature, and you go very slowly, you can actually cancel the friction, go into the thermolubric regime. There is another regime where the friction is viscous again, is if you go very fast. If you go very fast. Because if you go very fast, you fly over the potential landscape, and so you don't jump into the minima of the potential. And once again, friction can become linear with velocity. I call that ballistic when you go very fast. So the typical picture of a nano-frictional system is like this. At finite temperature, very low velocity, you can be thermolubric. Then you have a long regime, many decades of velocity, where you go stick-slip and the friction changes very little. And then eventually you can get to the ballistic regime, where you go viscous again. That's a rather important message to take home, because you can identify these regimes when you want. In fact, the thermolubric regime has been recently observed in this experiment at the École Normale, where they slide a gold tip on some surface, and when they go to the very small oscillation amplitudes, they see that the friction, instead of remaining constant, it would remain constant if it was stick-slip, goes down linear with velocity. So that's an observation of thermolubricity in their system. Thermolubricity is also interesting from another viewpoint, and that has to do with statistical mechanics, which I think is rather interesting for a physics audience. Suppose you do this Tomlinson model. In fact, you take two minima separated by a barrier, and you consider what will happen if you go back and forth by applying an external force. This is a simulation that has been done by many people. We did it once again because we wanted to understand what was going on. Again, Emanuele is involved in this one. It turns out that you can formalize this analytically, and you get an estimate for the crossover. What is the crossover between a stick-slip regime, thermolubric and thermolubric? What is it's not a sharp switch, but it's a crossover temperature. And not surprisingly, the crossover is when the work that you do per cycle is about kBt. So if your work per cycle is way above kBt, then you are in this in this regime over here. If it is very small, much smaller, you are in this regime here. That's this is the work divided by kBt. Right? You go from one regime to the other. There's more than this, as a matter of fact. And this is what I said is something interesting from the point of view of statistical mechanics. Suppose you are in a position, you have your slider in a position B, with very low energy, good position, but you want to take it to point A, where the energy or the free energy is different, is higher. And you go from A to B, A to B, A to B many times. Of course, if you do this, you have to pay. And how much do you pay? Well, at least you pay the difference of free energy between A and B. You cannot pay less than that. And so you would say, well, plus on top of that, there will be some dissipated energy. So the average value of the energy, of the cost, the work to be done by going many, many times from A to B must be larger or at most equal to delta G, the free energy difference in equilibrium. Okay. Then comes Mr. Jarzynski, and this is an amusing thing because it's a piece of thermodynamics which was discovered 20 years ago and not 200 years ago, as it should, who says, well, this is true. If you take the average value here, this will be larger. But if I take this average thing, so every time I go from A to B, I collect not WA to B, but I exponential minus temperature, the work done from going from B to A, divided by temperature, and I take the average of this over many, many rides, this must be identically equal to the free energy difference between the two. And as I said yesterday too, the first time I saw this, I thought Mr. Jarzynski has made a mistake. How can it be that if every time I have to pay more than delta G, then I take this stupid average and I get an exact equality? Well, of course, he was not wrong. I was wrong like hell. And what I had not understood is that even if the delta G BA is this value here, and the average value that I have to pay is larger than that, there still is a distribution. There is a distribution. I do this attempt at sliding many, many times, and there is a distribution of work exerted. The work that I have to pay is not the same every time. There are fluctuations that are related with temperature. And these fluctuations are such, must be such, that some of these times you actually don't pay delta G, you pay less. I call this a free lunch. And free lunches do not seem to exist here in Genoa, but they exist even here. They have to exist. They must exist for this thermodynamic equality to be obeyed. If you do any friction experiment an infinite number of times, some of the times, no matter how rare it could be, you have to pay less. Remember that if VA and B have the same energy, then then you will gain. You will gain energy from a few of these, few of these cases, the free lunches. In the macroscopic world, in the real world that we know every day, free lunches do not exist. But in the nano world, they exist and they have to exist, and they have been seen, and they are the clue. Thermodynamical reason for this equality to be obeyed. Emanuele himself built up this very amusing picture. It's a very complicated object. I want to spend a minute or two on this one because there is something we don't understand over here. And so maybe somebody in the audience has an idea. Emanuele consider this Tomlinson model. It does n trials, A to B, A to B, A to B. The energy from A and B are the same. They are two minima of the same model. So the delta free energy, delta G, is equal to 0. And then he plots, he collects a quantity which is called delta JE, which is this average. It's the average, this exponential average I was telling you before. Now, if you do n going to infinity, if you go from n to infinity, this delta has to be 0 because it is the free energy. It must be the free energy difference between A and B, which in our case is 0. So delta E is equal to 0. If I plot E, this exponential here, I must be on this line 1. If I do infinitely many attempts, I must be on this line 1. If I, on the other hand, do very few attempts, or else if the temperature is very low, then I do not have the chance to satisfy the Jarzynski identity because I don't do it enough many times. I do not collect enough free lunches. If you do not collect enough free lunches, you are on the left-hand side, and then you can go as far as 0. So you have this kind of universal curve you see here, going from 0 to 1, plotting this exponential here, and against a quantity which is normalized like below here, n divided by something. Well, it so happens that we were expecting this to happen, but what we did not expect is that all the curves fall very next to each other. Of course, they are different depending on temperature. High temperature would be deviating above. Low temperature would go very close to this limiting line. But what did we not expect is that all the curves are crossing in a single well-defined point. This central point, we don't understand it. At this central point, delta JE is equal to the KBT log 2, which happens to be the Landauer free energy that you have, work that you have to spend when you destroy an information, KBT log 2. Okay, it's true that we go from a valley to another, so it may have to do with crossing a barrier and deciding whether you go right or left. So that's where the log 2 comes, but we don't really understand it. So it would be nice to understand it. Okay. Let's see. 3. This means how much time do you think I should? Okay. Okay. So let me just come at least to cover some of these other paradigms, and then we'll be done. Suppose you have this model where I describe two systems that are out of registry with respect to one another. If they are out of registry, these periodicities are different. The energy does not depend on the relative position. You can convince yourself that if two quantities are irrational relative to one another, you can move them and the energy will not change. If the energy does not depend on position, then there cannot be friction, because I can move something, I would think, and I get to another state which has the same energy, so there is no barrier, so there should be no friction, so there should be free sliding. And this is what everyone believed until Aubry in 1983 showed that this naive supposition is not correct. It is not correct because it is correct if the interaction between two systems is weak enough, is strong enough, but if the interaction gets weak enough, it is no longer true. And the reason for that is shown by this picture here. If the springs are very strong, then every particle in this chain can occupy every position. And when you have that, the chains can slide and everything will be smooth. But if the springs are very soft, what will happen is that every particle will want to go to a minimum of the potential. No particle will want to go to a maximum of potential. And if you are in this situation, you can show it that the probability to find a particle in this maximum goes to 0 mathematically. And because of that, there is so-called broken analyticity. The energy is still independent of position, but there is a kinematic barrier, and you get stick-slip friction in this case. So that is a very, very sharp discovery. I remember Aubry was a student of my friend Robert Pic in Paris. And as I visited Robert Pic in the 70s, he says, I have this student, says Aubry. He's very bright. Unfortunately, he does stupid things, and I cannot convince him to do phonons. That is a real thing he should be doing. This shows what old people can tell their students, right? Aubry was doing something extremely important, which his supervisor, although a very knowledgeable and very bright man, would not understand. And Aubry did this because he wanted to understand things his own way. It's a good message for students. Do not throw away your ideas, even if sometimes they look crazy. The Aubry transition has not easily been observed. We made a prediction a few years ago that it could be observed in some cold ion experiments. We did not believe that anybody would ever do it, but it's good to propose something. But in fact, the experiment was done with cold ions. I think this was calcium plus or ytterbium plus, I forget, trapped by Powell traps, so a very delicate experiment done by at MIT. You a chain of few particles in a laser field, and then you move them, and you can describe the friction, and the friction is 0, 0, 0, and at some point it begins. There is, as function of corrugation, there is the onset of static friction signals the Aubry transition in this system. We then, encouraged by this, we thought we could do the two-dimensional case. In the two-dimensional case, the Aubry mathematics does not work. There is no prediction from mathematics. But we did a simulation, and we proposed that in 2 dimensions, this could be a first-order transition. There would be a sliding phase, there would be a locked phase, but there would be a region of coexistence due to first order. We even predicted a critical point. At some sufficiently large temperature, the two, this is like a van der Waals coexistence curve in the liquid-gas transition. There should be a critical point. Where the experiment was done, we convinced Bakinger to do the experiment, and it is true. Where you did it, it was an emulation now. This experiment was an emulation, like the other one of the MIT experiment. They were emulations. You use colloids instead of a real lattice. You use a pattern surface instead of another lattice. You use lasers to pick up and photograph and things, and you can measure the friction as you try to move, and the friction is 0 up to a certain corrugation, and then it jumps up like this. So there is the Aubry transition does exist in 2 dimensions too. In this particular case, it is first order. So we're very happy that emulations exist, because they demonstrated that that what we had obtained by simulations was correct. And then we have real simulations. Here, the simulations that we do may be simple or complicated, but just illustrating a phononic friction. Suppose you want to move this blue particle by applying a force through a spring. The force will grow with time, but the particle will not move because it feels there is a lattice underneath, and the lattice will prevent the sliding. The force will grow, and it will grow, and it will grow, and it will go. I hope it decides to move. At some point, it reaches the static friction threshold, and when that is reached, you get a sudden drop in the force, and then the particle moves forward by one lattice spacing, and you get phonons irradiated away. That's a case of atomic stick slip for you, with the generation of phonons. Of course, because of the periodic boundary conditions here, phonons go back and forth and so on. And we do simulations of this type. This, for example, is a simulation of ballistic kicking a cluster of a graphene surface, or simulating the sliding of a graphene plate on top of this, and so with simulations you can do a lot of things. I think I will try to wrap it up very quickly now, because so there will be no time to describe the sliding of the graphene on layer on top of one another, but I think for the introduction this might suffice. I want to show you just only one thing, how you do spectroscopy with friction. So suppose you have a lattice, here it's 2-dimensional, that has a phase transition, a structural phase transition, and you do some sliding on top of this lattice. You can simulate the friction, and you predict there would be a frictional peak at the transition of the lattice. So you slide on something. This something is not a vegetable. It is something that has a phase transition. As you slide, you hit the temperature. Close to this temperature, there will be a peak in the friction. We predicted this, and we tried to encourage our experimental friends to do an experiment. They did it on strontium titanate, and they indeed found a peak. This is the antiferrodistortive transition of strontium titanate at 110 or 115 Kelvin. They found a peak in their nano friction, pendulum friction, actually not touching the substrate, oscillating above, which does correspond to that. I think this is more or less what it is. I will skip the rest, but we've done a lot. Our student, Jin in particular, has done a lot of simulations of sliding of graphene on top of one another. You get this moiré. The moiré is moving. to people that do the twisted bilayers of graphene, this might be interesting because the mechanics of these bilayers is influenced importantly by this. So if I can now switch over to the end of the talk, I think the end of the talk is just an end. So there is not much that I would like to add except to draw the summary. So at the nanoscale, friction has a lot of new things to say. Simple models are very important. They demonstrate not only basic facts, but they also illustrate paradigms. There is superlubricity, which I did not talk too much about, Aubry pinning, thermolubricity, Jarzynski and free lunches, and there was even quantum effects, I'm sorry, that one can do. And in the end, the theory is still under construction. The main difficulty of theory is similar to what we found this morning in the group of Giulia Rossi and Riccardo Ferrando. Namely, when you have a very complicated system, how do you extract a few important variables? There are so many damn variables there, and only few are important, but who tells us which are these few variables? Also, once we have these few variables, who gives us the equation of motion of these few variables? Same problem for everybody. Every one of us is trying to solve it in one way or another, machine learning, Markov state model, this and that and the other. Eventually, we will get to maybe a unified approach for all of us. Thank you very much.
We have time for questions. Any questions from you? No, I can start myself. About Jarzynski equality, is there any assumption about the distribution of the work that you have shown? Because you exponentiate and you get the same value, while if you don't, you don't get. Okay. Is there any assumption? Or?
Apparently not. It has been proposed. It has been elaborated and proposed not only by Jarzynski, but Gallavotti, people instead. Apparently, it's supposed to be completely general, but you have to really go to the bitter end of it. You have to go an infinite number of times. If you go for an infinite number of times, the sampling of the system will take place according to the holy rules of statistical mechanics.
Essentially, you have to sample exponentially unlikely paths.
Exactly. So the assumption, what makes it very difficult is that there are regions that you will, with extreme difficulty, it will, as you say, it will get exponentially difficult to sample. So if you have a creaking door, you might expect that this door might sometimes move spontaneously because of a thermal fluctuation. It will not happen in the course of our lifetime because the system will not sample that. But so far as I know, it is absolutely general.
Okay. Any
distribution is related to what? The weight of the distribution is related to what physically?
I guess it must be related to the energy profile and many other things. But then you will have the tails, right? And the tails always will have, I think, a well-defined exponential behavior, or Gaussian, I think, for behavior eventually. As you go into regions of that are very unfavorable energetically, then you get the sampling of these very energetically costly regions in a way that will give rise to the characteristic type of population. The width, I think, has to do with the form of the potential that you have. Because suppose you had well, we can discuss that, but I think it has to do with that.
May I? Another question. In the results you have shown, sorry, as a function of velocity, you are using a reduced velocity. reduce in terms of what?
Let's see. Let's go back to. You refer to. Is it this one? No.
No, yeah, this one, for instance.
This is absolute velocity. What do you say? Absolute reduced.
Well,
Actually,
10 to minus 2 what?
Okay. So if you wish, this velocity here is the frequency with which you switch back and forth between one layer and the other. It's the frequency, right? Obliges you to translate into an effective average velocity with which you move from one side to the other.
Sono le scale così.
You showed us these experiments about the friction between two layers of graphene or van der Waals materials.
I'll try to keep it moderate because I had probably too much material about that, but I'll just show you something.
And
Okay, so,
Okay.
yeah?
And very recently, there was this paper from the group of Schala, and they developed this quantum twisting microscope. So they have one layer of van der Waals material, and then on top of an AFM tip with a pyramid with a plateau on it, they put another van der Waals material, and they can push the two van der Waals material close with each other and rotate while doing their measurements. So I was wondering if this kind of device may be useful for studying friction.
Absolutely. See, what you see over here, sorry. You see what the right-hand side here is a flake of graphene, which is twisted by an angle. You see it from the moire, right? And this one is being pushed forward. What I intended to show with this picture here was that if you don't have a flake, but you have an infinite system, the motion of the if you don't have boundaries, the motion is without friction, it just moves smoothly. And if you have a boundary, you can move in a way which is not completely smooth because the moire has to enter and exit from the boundary. You could also do this. In fact, I don't have it here to show to you, but we also simulated the turning around. And we have a paper now out showing the combination of turning and pushing. How does the deepening threshold change if you try to push, or you try to turn, or you try to do the two things at the same time? And there is a behavior in these incremental systems that is rather different from the one classical system. I assume that at this stage there are many people that are doing rather similar things in this area. So maybe the paper that you refer to has something similar to the kind of thing. These things we did by simulating the system I was showing a moment ago. With the Chigua and
Thank you very much.
Any other question? No, I don't see. So we can thank again.
Thank you. Come si fa a spegnere qua? C'è un concettino.